I love finding the volume.
Figures.
Yeah, of composite figures.
When we have objects that are based on multiple other figures, it's not so bad for finding their volume overall. We can break the whole object into basic figures, and then find the volume of each one of those pieces, add them up, and to be quite honest, it's way more fun than surface area.
I'm telling you, that's why I love it.
Figures.
So, we are going to look at this first shape. We can see that it's composed of multiple things put together. This thing, that thing, the thing over here. Well, this top thing is really just half a sphere. This middle thing, just a cylinder. And this bottom thing, a cone. And now, to find the volume of this, it's not really that crazy. What we're going to do is find the volume of half a sphere, the cylinder, cone, add them together, call it a day. So here we are. So I'm going to say volume is equal to, I'm going to write it in words, volume of half a sphere plus volume of cylinder plus volume of cone. Now, what you could do is you could say, well, I'm going to find all of these separately and then add them all together. What I'm going to do is I'm going to just do it in one long piece and do it in one big step. And then maybe Mr. Thud will do the next one in 3 separate. And you could kind of pick what seems best for you.
Oh, it's not going to be a maybe.
Oh, alrighty. So, taking a look at this, maybe what I'll do is I'll color code these so that we can still see them as separate entities if we wanted to do them as such. So, for the volume of half a sphere, I'd have half times the volume, and a sphere's volume is 4/3 pi r cubed, not squared. Then a volume of a cylinder, what color did I do that? Volume of the cylinder was my area of my base times height. And this height is specifically for the cylinder because realistically, the area of the base for my cylinder and my cone are going to be same because they're sandwiched against each other. But notice they have very different heights, right? Here, the cylinder has a height of 24 meters. Here, the cone has a height of 10. So that's going to be different. So we're going to want to note that. And, of course, my cone, my volume there, I did in orange, is 1/3 the area of the base times height, and that's going to be of my cone. Okay. Again, I didn't denote these B's or these area of the bases to be different because, again, they're sandwiched together, so they will be same. Just for the sake of plugging all my values in at the same time, I'm going to do the same thing here in my second line for my half sphere, but I'm going to change my capital B's to be more specific to the shapes that I have. So my capital B stands for the area of the base. My base of a cylinder is a circle, and so I'm going to have pi r squared. Notice that this r, and eventually the r we'll get here, spoiler, is going to be same. The only thing that differs here will be my height. Alright, so that is my volume of my cylinder. My volume of my cone, we have 1/3, we have pi, we have r, and we have squared because that area of my base is a circle. We get pi r squared. And then we still have it times height, but now again that's specific to my cone. Alright. Now, I'm going to plug in all these values. Yeah, I am. But I wanted those equal signs to be purple. Okay, so I have 1/2, I have 4/3, I have pi. What is my radius? Well, taking a look, I can see my whole diameter is going to be 12. My radius has half of that, so it's going to be 6. And I don't have to see that calculation for the radius. It is kind of assumed that you know how to figure that out by now. If you want to show it, cool, but it is not absolutely mandatory. So that is my plugged in values for my half sphere. For my cylinder, I have pi. My radius is again same. It's going to be 6. And my height of my cylinder is this 24. And then, of course, I have my volume, my cone. I have 1/3 pi. I have 6 squared. Now my height here is going to be 10. And here we have it, 10. Now, when I plug these values in, I can go ahead and straight up plug these into my calculator. When I do this calculation, I have 1/2 times 4/3 times 6 cubed. And when I do that, where am I? I believe I get 144 pi. Okay. And the next one here, when I get 6 squared times 24, I have 864 pi. And in purple. And last but not least, for my volume of my cone, 1/3 times 6 squared times 10, well, that will give me 120 pi. Now, I'm going to go ahead and collect all my like terms, which are all of them, because they all involve pi here. And when I go ahead and do that, I end up with 1,128 pi. Now, one thing to note is that the question didn't say didn't specify if I should be looking for exact or approximate volume. So the rule of thumb that we're going to follow is if it doesn't state, it's always going to assume exact. You could see that in the question it'll either say to round your answer to the nearest hundredth. That would then imply approximate. But if it does not state, we're going to leave it as exact, which means over here, all we're missing are our units. And the units here, all our values were meters. Since this is volume, we're going to have meters cubed. Woof, that was fun. A party indeed.
Every party needs a cake.
Encore, encore. Oh, legit cake, wow.
Yeah, like legit cake. Like this cake. I'm going to turn the volume of this cake.
Oh, yeah.
Really having just trouble scrolling here. That's fine. So, all of these things have a height of 8 centimeters. So, this is 8 right here. This is apparently also 8. And this is apparently also 8. Apparently this thing is not drawn to scale. That's my bad. But anyways, the slabs have diameters 12, 26, and 40. So, the smallest one is probably the 12. This next smallest one is probably the 26, and then this largest one is the 40. And we're going to determine the volume of this whole cake. How much Betty Crocker mix was put into this. Man, I really like to put out a shout out to like Get Sliced with Eleni or anything in here, since she's an SMA student. This is an SMA video. I don't know.
Yeah, she makes some great cakes.
Can show her this to her. I don't know if she got the shout out. Any case, when I approach something like this, I like to personally separate things into the components. That I have this first figure that has a volume, and then I have the second figure that also has a volume, but they're not the same volume, so I can't just say V and V. So just as up here, where Miss T noted that we have like the height of a cylinder and the height of a cone, we have those little subscripty business things, so we can indicate what's what. Similarly here, I'm just going to call this V1 and call this next one V2. So we're talking about the first slab, the second slab, the first volume, the second volume, and over here, the third volume. So we use those subscripts to our advantage, just like that. Then when I talk about them, I can talk about the volume of the first slab as being base times height for that. And I can figure out the volume of the second slab, which is also, I guess I should say base 1, base 2 for volume 2. And I can find the third volume as base 3 times the height. Oops. So noting, I'm using that subscript for the bases because all those bases were different. I'm not doing it for the heights because the heights are all the same. So if they're the same value, you can use the same variable. But if they're not, then make sure you're switching that. Any poopsies? Now I'm going to find this. So my first volume, base is pi times the first radius squared times h. That first radius was, whoa, I don't have it. But diameter is 12, so the radius must be 6. And the height is 8. So for this whole thing, that gives me 288 pi centimeters squared. Oh, try again. Cubed. That was close. Second volume, base 2 times height. Base 2 is pi times the second radius squared times the height. That second radius was not 26, that's diameter, but 13. And the height is still 8. All in all, volume of that middle slab is 1,352 pi cubic centimeters. And this last one, again, volume is base 3 times the height, where base 3 is pi times the square of radius 3, and then the height. And then our third one, diameter was 40, so we're looking at a radius of 20, and multiplying that by the height again. So that bottom slab has a volume of 3,200 pi cubic centimeters. I'm not done yet, but I've gotten the volume of each of these individual components. That looks like a snowman. And now that I've got those two components, I can put together the total volume. Where my volume is the combination of V1, V2, and V3. Which, for us, if we add all those together, gives 4,840 pi cubic centimeters. This thing is done. That's all looking neat and tidy. And once again, just as Ms. T mentioned, we're not providing the approximate one in this case because it wasn't specified, and we're assuming that to be, meaning that we need the exact volume. I wonder what the next page has.
Oh, is that more practice work? Hey, that's the aquarium you gave Mr. O'Donoghue.
Yeah, you can see it in the physics lab still.
Oh, dang, cool. So check these next questions out, give them a go. Ask questions if you have. The answers are provided at the bottom. We are reaching the end of our topic. So we will be having a test pretty dang quick. We'll tell you all about it in class. And that's it for now. Have fun and math safe.
All math is safe, isn't it? I don't know. Math is great. I don't know. I love math. Could probably stop this now. Yeah. Do you think anyone's still listening? Do you think anyone's still listening to this video?
I'm not.
It's okay. I'm very easy to tune out, I'm told. What if the students are tuning me out right now?
Oh my gosh, just stop the video.